Hello, welcome to this lesson. In this video, you are going to learn how to find particular solutions to differential equations. So I have this example here which I'm going to use to explain to you how to find particular solutions to differential equations. So I will rewrite the question. We have 1 plus cosine of 2 theta multiplying dy theta equals 2. So the first thing I'll do here is to carry out separation of variables, okay? And to do this, first of all, I will separate the differential coefficient. So I will take the theta to the right hand side, which will give us 1 plus cosine of 2 theta multiplying dy equals 2 d theta. Okay, so from here, I will want to group like terms, okay, so that we can continue with integration. So to group these like terms, I will divide both sides by 1 plus cosine of 2 theta, 1 plus cosine of 2 theta. Okay, so I can cancel out this. So from here on the left hand side, you're going to have 1 dy equals 2 divided by 1 plus cosine of 2 theta d theta. This is what you're going to have. But what I want to do is that I want to get rid of the 2 on the right hand side, okay? So that on the right hand side, we can only have the terms with the theta there. Okay, so let's look at what you're going to do. So I'm going to multiply both sides by half, this side also by half, okay? So these two will cancel out these two. Then at the end, we are going to have 1 over 2 dy equals 1 over 1 plus cosine of 2 theta d theta. Okay, so this is what you are going to have. Okay, so from here, we can introduce the integral symbol. Okay, so let's look at that. So you're going to have the integral of 1 over 2 dy equals the integral of 1 over 1 plus cosine of 2 theta d theta. Okay, so integrating this term will be a little difficult. Okay, so for this reason, I'm going to use a double angle identity, okay, so that I can rewrite the term, that's the denominator here. Let's look at that. So if you have 1 plus cosine of 2a, okay, that would be the same as 2 cos squared of a. Okay, so I'm going to use this in place of what we have here. So I'm going to have the integral of 1 over 2 dy equals the integral of 1 over 2 cos squared a, sorry, not a, 2 cos squared theta d theta. Okay, so from here you can see that you can separate the half from this term here. That's the term on the right hand side. So you can have something like this, half 1 dy, okay, you can have something like this equals half the integral of 1 over cos squared theta d theta. Okay, you can have something like this. Okay, so the half multiplying the integral of 1 dy is the same as what was here. Okay, it's the same thing. So from here you can see that the halves can cancel out, so that we have the integral of 1 dy equals the integral of 1 over cos squared theta d theta. This is what you're going to have. Okay, so at this point, to make the integration simple, I'm going to introduce another identity. Okay, so let's look at that. So you are going to have this identity 1 over cos squared of a, okay, to be equal to sec squared of a. Okay, so I'm going to use this identity for the term we have on the right hand side so that the integration will be easy for us. So let's look at that. Okay, so we are going to have the integral of 1 dy to equal to the integral of sec squared theta d theta. Okay, this is what you are going to have. So now let's perform the integration. The integral of 1 with respect to y will be y, then that will be equal to the integral of sec squared theta with respect to theta, that will give us tan theta. Okay, and then you can bring the constant of integration. So what we have here is the general solution since it contains the arbitrary constant. And we want to find the particular solution since we've been given some boundary conditions. So let's look at that. So we were given that y equals 1 when theta equals what? Pi over 4. So you can substitute this into the general solution so that we can get the particular solution. So let's look at that. We're going to have y equals tan theta plus c. Since we want to find c, we can make c the subject. So we're going to have c equals y minus tan theta. Okay, so let's look at that. So we are going to have 1 minus tan of pi on 4. Okay, so let's do that and see what you get. So first of all look at tan of pi on 4. Okay, so when I compute the tan of pi on 4, that gives us 1. So then we are going to have 1 minus 1, which would be equal to 0. So and then the arbitrary constant c will be 0. So you can get our particular solution, which is the solution without the arbitrary constant, to be y equals tan theta. So this becomes the particular solution to this differential equation.